Hey, it's Mr. K doing a video for AP Physics 2, and just 2 this time. So let's go ahead and talk about a lab that we're going to spend about 2 class periods doing. It's a very important one that lets you kind of see electric fields or how they interact, as well as another thing called equipotential lines. Let me go ahead and write that down on the paper here. So let's transition to that. So equipotential lines, and what that's going to represent is imagine you had like a cliff or like a waterfall with many different levels that you can fall down to. So like you have the whole thing, which is like 100 meters tall, and then you got like a little cliff face at like the 70 meter mark, and then another cliff face at like the 20 meter mark, and another cliff face at the 10 meter mark. You could draw an equipotential line for all those. So if you've ever seen like an elevation map, one that like a map that kind of shows you the lines where all the elevations are the same, where all the heights are the same. That's kind of what I'm talking about. So we're gonna do that for voltage, and it's one of my favorite labs to do with Physics 2 because it kind of shows you something that usually it's just all imaginary for you up until that point. So hopefully it'll be that. So what we're gonna do is we're gonna go in and we will fill a tray with water. It's gonna be like a cake tray, and then fill it with about a centimeter of water, put in 2 conductors, and this is what these are here, into the water. Yeah, I know, electricity and water. I'm still gonna do it. And we're gonna put the voltage source, one of those power boxes, and connect the positive side and the ground side to either one of the conductors. I'm gonna set it to around 20 volts. If 20 is too high, we'll set it to 10 volts. Whatever we can, really. I'm gonna use 20 as an example here. And what's going to happen is that one's going to be positively charged, the other one's going to be not as charged, or vice versa. And there's going to be a little trickle of electric charges that go across. And it's going to set up an electric field as well. So we're going to have an electric field going from one of these bars to the other. And if I say that the left bar is 20 volts, what I know from the equation of voltage, which we'll write down over here, voltage is KQ over R, voltage from one point charge. And if that point charge is positive and we're really close to it, this would set up a positive voltage for me. So if I've got a positive number here, I would bet that this is going to be positively charged compared to the other guy, which would be negatively charged or not charged. So let's start with that. So let's say that this side is positive charge, and this side will be negative charge. And if that's the case, what we're going to get here is electric field lines that go across it from left to right. Electric field goes away from positives and towards negatives. And so we should be able to see this as a result of your experiment. So I'm kind of shortcutting it right now. These lines are going to appear on your diagram after you've taken all your data, after you've gone through the majority of the lab. So I'm showing you what the result should be. What's going to happen on the ends here, though, is that we might get a little bit of bowing outwards. So as we get farther out from these parallel plates, this electric field line should actually bow a little bit because, let's say I pick the spot out here. If I pick this spot out here, my electric field should go away from my positives and towards my negatives. And if I pick the spot over here, my electric field again would go away from my positive and towards my negative. But this field is going to be a lot stronger. So you can kind of imagine that we'd have a little bit of bowing on the side. And hopefully we get that in the lab itself. And so that's what the electric field should look like overall. So I'm going to use these squares as 1 centimeter each, because that's what they actually are in real life. And let's see if we can actually work through that. So back to electric field. If we remember, electric field is going to be KQ over R squared, which is great. But there's a small problem here because these 2 equations are based off of a singular charge creating a potential at a point, or a singular charge creating an electric field at some point away from it. What we have is not a singular charge, but we have a multitude of charges. So what we might want to do is we might want to look at another version of these where if you look, they're very, very similar, right? So the only difference is that V, the voltage, does not have a square on the R. So it's kind of like we took the electric field equation and we just kind of multiplied it by a distance. And it turns out that that's actually what we can do here. So an equation that we're going to use is a voltage difference, we always need a difference, is going to equal the electric field applied over stretched over a certain distance. All right, so if you look at your diagram, we do have electric field. It is stretched over this distance, and then we can actually figure out maybe what the field strength is. So working kind of backwards in the video that I'm showing you right now, in the lab you're going to be going in and finding voltage levels at different points between the two conductors, and then at the end of your lab you're going to end up with something that looks like this. So we're going a little bit backwards forwards here. So if I'm going to sneeze. Excuse me. If we look at this equation alone, the change in voltage is ED. All right. So electric field times the distance that we go. So if I go from all the way left side to all the way right side, my change in voltage is negative 20 volts. Okay. And that would say that this is equal to some electric field for this distance, and this distance, like I said before, was 1 centimeter per square, so that's 10 centimeters there, and so that's going to be 10 or 0.10 really for the distance in meters. And then if we divide over, we can say, all right, that negative 20 change is going to be divided by 0.1 meters, and that's going to move my decimal over again, so I'm going to have about a negative 200 newtons per coulomb electric field. That's going to be set up between these parallel plates. Now, if we were to talk about the direction of the field, again, thinking that it should be going to the right, if we have this change in voltage from left to right. Got the negative 20 there, so kind of curious about that negative 200, so again, a little curious about that. But pretty sure that if we have a 20 volt thing over here, the higher the voltage, the more positive the voltage, you're around positive charges. Positive charges want to go more towards negative charges, and so we should have electric field lines going from left to right. Okay, so if that's the case, what we can do is we can say, all right, what about here? Okay, if we talk about the voltage in the middle, if this is 20 and this is 0, then the voltage right in the middle should be 10 volts, right? Well, what I can do is I can talk about anywhere really in the middle, and that should be 10 volts, 10 volts, 10 volts, and 10 volts. Okay, if we're looking at a constant change of voltage from left to right. And what this is going to do for me is it's going to set up a line of voltage, a line of equal voltage that kind of looks like this, or an equal potential line, If I go, let's say 1, 2, 3, at this point here, that would be equivalent to 20, 19, 18, 17 volts right there. Down here would also be about 17 volts. Down here would be about 17 volts. And up here would be about 17 volts. There would be another equal potential line that would all be around 17 volts like so. Now as we get farther out from the center, outside of these conductors, we're going to start to see these values kind of curve it back like that. And this is in the ideal case. I know that in the real world we're going to have a little bit of a variation here. But this line here would represent about, not 19, not 18, but about 19.3. So this is going to be a 19.3 volts there. Actually, wait, not 19.3, 18.3. Sorry. And this will be 18.3 volts down here, and this will be about 18.3 volts down here. And so what you're looking at again is like, it's like a waterfall. You have the top of the waterfall, you got the bottom of the waterfall, and you might have all these platforms in between, and the charges can jump the whole distance and get all that energy from the waterfall, or it can jump just one distance. But depending upon how much it jumps, it's going to get a certain amount of energy depending upon the difference in voltage. And so if you keep on doing this, now what you're going to be using is a multimeter, and you're going to be placing the probes on a conductor and then somewhere in the water and reading the multimeter reading in volts, in voltage. And you're going to find out all the different positions where the voltages are the same. And what that should do for you is set up these lines of equal potential. And what you should then notice is, let's see, this would be 1, that would be 2, so that would be like 1.8, 1.7. And this is going to be 1, 2, 3, so this line's about 3 volts. Wait a minute. Not 1.7. Each square's got to be, this is 20 volts down to 0. My bad. Yeah, all these are a little bit different. So this is actually 2, this is going to be 4, so this is going to be about 3-ish. This is going to be more like 6. Forgot what I was talking about here. Same thing over here. This is not going to be 18. This is 18. This is going to be more like 17-ish. My bad. Anyways, so all these lines are of equal potential, and what you should notice is that the electric field lines are perpendicular to those, and that's rather neat. So if we have a charge, let's say we have a positive charge up here, where does that positive charge want to go? You know, it wants to get away from other positive charges, it wants to go towards negative charges. It's going to want to go this way. Imagine this like a big hill, right? And that hill is sloped downwards. Positive charges want to go down the hill towards lesser potentials or negative potentials. Negative charges, on the other hand, being negative, want to do the complete opposite. They're going to want to go up the hill. All right? And so we should be able to set up this equipotential map based on the different voltage readings that we get between these two conductors. That's not the only thing that I want you to do, though. You're also going to set up something that might use a bar on one side, and maybe you have just a point on the other. And if that's the case, if the bar is all positive, 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 what your electric field line should look like, if this is your negative side, is something that goes like this. I'm going to use, again, the same colors. So right in the middle, we should see an electric field that goes straight across like so. And the value for the electric field here might actually change depending upon how close we get to this other charge. Here, the electric field stays pretty constant between the two plates. But then we should get something that kind of does this. And if it does that, the way that we're going to get this shape is we're going to take voltage readings, and these voltage readings should look a bit like this. And you're going to see a little bit of curvature here in order for the electric field lines to be perpendicular to your, actually it's going to go like that, in order for your electric field lines to be perpendicular to your voltage lines, your equipotential lines. We're going to have multiple shapes, and we'll talk about what the structure looks like as far as the setup of the fields go in class. So stop here, and hopefully we get some good results in class.